Hello friends, I hope you're all fine. Today's lecture is about logarithmic functions. It is section 2 in chapter 4 of your lecture notes. Before coming to logarithmic equations, logarithmic functions. I'll make a quick review of the previous section. In the previous section, we talked about exponential functions. There is a relation between exponential functions and logarithmic equations. That's why I'm gonna give a quick review to that exponential functions. Exponential functions. We said what are exponential functions. An exponential function is a function written in the form of b to the power of x. We said that b is called the base, okay? It's called the base for the exponential function. And that base must be something that is greater than 0 and not equal to 1. So what are the conditions for a function like that to be an exponential function? We must have that number here, b, the base, must be something positive and not equal to 1. And that x in here, which is making the domain of the function, takes every value from the real numbers. So that means the exponent that I have got for that base takes positive, negatives, rationals, and irrational numbers, okay? In general, that's the domain of the function. About the range of the function, the range we set, whatever we're inputting in the function, we get something that is from 0 to infinity. That is the range for the function. We sketched the graph of the exponential function. We said it is something like that. The y-intercept is from 0 to 1. Okay, that's something b to the power of x, where the base is greater than 1. We said in general that exponential function is continuous, it's smooth. If b is greater than 1, it is increasing. If b is less than 1, or we can say between 1 and 0, it is decreasing. We said the intercept is 0 and 1, the y-intercept. The range is between 0 and infinity, and so on. We had some properties for exponential functions. We said if you have got b to the power of x, that's equal to b to the power of y. That is definitely true if and only if x is equal to y. If you've got b to the power of x multiplied to b to the power of y, we said that's true if when the bases are equal to each other, the powers will add to each other. We had b to the power of x divided b to the power of y. That's true, or we can say that equals to, not like that, okay? That equals to b to the power of x minus y, and so on, okay? We had some other rules. For example, if you have got b to the power of 0, b to the power of negatives, how do we deal with them? We had some properties for exponential functions. Today we are coming to the logarithmic functions. There is, of course, a relation between logarithmic functions and the exponential functions, as they are inverses of each other, and we will move to that thing later on. First, let's give a definition to logarithmic functions. What is a logarithmic function? Okay. How is it written? In general, we say that y, that's equal to logarithm of x with the base of b. That's true if and only if, okay, I will write if and only if like that. B to the power of x is equal to, b to the power of y, sorry for that. B to the power of y is equal to x, okay? Of course, let me come to the definition of a logarithmic function. When we are saying that this is the symbol, the writing form of a logarithmic function, that base of the logarithmic function again must be something greater than 0, okay? And of course it's not equal to 1. So again, when we are talking about logarithmic functions has got base, and that base must again be something greater than 0 and not equal to 1, okay? The x that I have got here is making the domain of the function. What are the values that this x take? This one takes positive values, so it takes values that are greater than 0. So we can say that the domain for a logarithmic function is from 0 to infinity, and the range is the set of all real numbers. Okay, so if you have got a logarithmic function written in the form y is equal to logarithm of x with the base of b, we can change it back to an exponential function like that, b to the power of y is equal to x. Or if you have got b to the power of y is equal to x, we can form a logarithmic function. Okay, so that is the logarithmic function with the condition on the base and the domain that is taking the positive numbers. Let's come to the examples that are given in your course material. We've got example 4.2.1. Okay, it says evaluate the followings. Evaluate. What do I have? The first thing I have got logarithm of 1000 with the base of 10. It is required from me to find that value. Okay, what is this one equal to? I have to find that value. Of course, you do not have a calculator, so what do we have to do? We have to calculate it. We have to find a way so that we can find that value. How can I find that value? I know that if I have got a logarithmic equation, I can change it back to an exponential function, and I know the rules of exponential functions, so I can deal with it. Okay, 10, how can I change a logarithmic function to an exponential function? I will say 10 to the power of what is equal to 1000, like this one, b to the power of y is equal to x. Here, I will say 10 to the power of that question mark, that's equal to 1000. This is what an exponential function. So now here, we are trying to solve that one, evaluate that one using exponential rules, properties. Okay, 10 to the power of what is equal to 10 to the power of 3, because when I'm dealing with exponential functions, the bases must equal to each other so that I can say the powers are equal to each other. So 10 to the power of what is equal to 10 to the power of 3, since the bases are equal to each other, so I have got that what is equal to 3. So what is the result of this one? It is equal to 3, because we found the question mark and the question mark is equal to 3. Let's move to part B. I've got logarithm of 32, that's equal with the base of 2. It's required from us to find that value. Okay, what is the value of this one? Again, I'm doing the same procedure, changing the logarithm back to the exponential function. So I will say 2 to the power of the question mark or what, that's equal to 32. 32 is 2 to the power of what? That's 2 to the power of what is equal to 2 to the power of 3 is 8, 2 to the power of 4 is 16, 2 to the power of 5 is 32. Now, according to the rules of exponential functions, if I have got b to the power of x, that's equal to b to the power of y, bases are equal to each other, so the powers must equal to each other, so the question mark is equal to 5. So what did I find here? I found the result of this one, and that's equal to 5. The other example, we have got part C, logarithm of 1 over 125. Okay, that's not a power. Okay, it's inside the logarithm with the base of 5. It's required from us to evaluate this one. That means finding the value of that bit. Again, we are doing the same procedure. I will change this one. Okay, 5 to the power of what is equal to 1 over 125. I'll calculate this one. I have to change this one to something of 5 to the power of something because I'm dealing with exponential functions. Okay, 5 to the power of what is equal to 125 is 5 to the power of 3, but since it is in the denominator, I'm putting it up the numerator, so that will be 5 to the power of minus 3. Okay, because 5 to the power of 3 is 125, the minus brings it down, I'll get 1 over 125. Okay, so since the bases are equal to each other, so the powers must equal to each other, so I get that the value of this one is negative 3. That's the basics of logarithmic functions. We have got another example. Again, it's for evaluation of the unknowns. Okay, 4.2.2. It says evaluate or solve for x. I will write it simply, solve for x. That means find the values of x in the given expression, mathematical expression. I have got the first example. It is logarithm of x with the base of 4. That's equal to 1 over 2. Okay, part B. I have got logarithm of 16 with the base of 64. That's equal to x. What's required from us here? To find the value of x, finding that unknown in the function. Here we only had this one and that one was given to us. It was required from us to evaluate the logarithm, but here the x is moving. Once it's here, once it's there, and one it will be the base of the logarithm. Okay, so let's calculate this one. How can I calculate this one? Again, by changing it back to an exponential form. So I will say 4 to the power of 1 over 2 is equal to x, okay, because I know that if I say 4 to the power of 1 over 2 is equal to x, it will be changed back to an exponential function. 4 to the power of 1 over 2 is equal to what? That means 4 under the square root is equal to x. So x is equal to what? X is equal to 2. And that's the result for that x. So if I put instead of that x2, I will get 1 over 2. Now, let's move to that one. Again, I have got a logarithm. I have to change it back to an exponential function so that I will find the value of x. 64 to the power of x is equal to 16. 64 is 4 to the power of 3, okay? And it is all to the power of x, and that's equal to 4 to the power of 2. Now, since I have got with the rules of exponential, this one multiplies to that, so that one is 4 to the power of 3x. That's equal to 4 to the power of 2. Again, the bases are equal to each other, so 3x is equal to 2. The powers will equal to each other, and x is equal to 2 over 3, because I'm dividing both sides by 3. Okay, now that x is equal to 2 over 3. Let's move to part C. I'm given logarithm of 27 with the base of x. That's equal to 3. Okay, what does that equal to? Again, I have to change this one back to an exponential form. So x to the power of 3 is equal to 27. I have to change the 27 to something to the power of 3, okay? Because if the powers are equal to each other, the bases will equal to each other also. So x to the power of 3 is equal to 3 to the power of 3. Here we don't say that the bases are equal to each other, so the powers will equal to each other. Here the procedure is opposite. We say the powers are equal to each other, not opposite, of course. Then the bases must equal to each other. So x is equal to 3. So what's the value of that x given in here? It is equal to 3. Okay. We have got some logarithmic rules, like we had some rules for exponential functions, the power rules, the multiplication rules. We are having some properties for logarithmic functions also. So we have got logarithmic rules. I have got first functions defined. In general, I can say that, let me write it in another way. I have got logarithm of 1 with any base, okay? That's equal to what? That's equal to 0. That's always true. For example, if I have got logarithm of 1 with the base of 2, it's equal to 0. Logarithm of 1 with the base of 10, it is equal to 0. Logarithm of 1 with the base of 100, it is again equal to 0. So whenever you have got that one here with any base, of course the base has got its conditions, that it must be something greater than 0 and not equal to 1. So with any base, when I have got logarithm of 1, that's equal to 0. The second rule is that I have got logarithm of b with the base of b, that's equal to 1. Okay, again, that b has got conditions. It must be something greater than 0 and not equal to 1. So whenever that number and that number are equal to each other, the result is equal to 1. But of course, I must consider the conditions on the b, the base that I have got. Okay, the third one is called the equality rule. Okay, equality, or let me write the kind of rule. Equality rule. I have got logarithm of u with the base of b is equal to logarithm of v with the base of b. If you look at those two logarithms, I see that their bases are equal to each other. Logarithm of u is equal to logarithm of v, like we did for exponential functions. Since the bases are equal to each other, so u must equal to v also. Okay, this one must equal to this one because everything is the same, so these two shall also hold. Okay, this the fourth rule, it is the product rule. What is the product rule? If I have got logarithm of u multiplied with v, with the base of b, of course, multiplication changed to addition, so that will be logarithm of u plus logarithm of v, with both with the base of b. Of course, if I have got addition between the logarithms, okay, it will change back to multiplication. But please, I do not have this one. Okay, students always make mistake. Logarithm of u plus v, okay, it is never equal to logarithm of u plus logarithm of v. Okay, that is always wrong. Okay, addition, I have got nothing in logarithm that changes addition to something else, but I have got something that changes multiplication to addition. Okay, the other rule that we have got is the power rule. Okay, I have got logarithm of u with the power of r, that's equal to what? That power comes in front. Okay, so that will be r logarithm of u with the base of b. That r that I have got here is in the real numbers. Any power, positive, negative, rational, irrational, it comes in front of the logarithm. We have got another rule. It is called quotient rule. In quotient rule, I have got division changed to subtraction. So logarithm of u over v with the base of b, that's equal to what? Logarithm of u minus logarithm of v. Okay, so multiplication changed to addition and division changed to subtraction. But again, I do not have any rule that separates negatives. Okay, that is never equal to logarithm of u minus logarithm of v with the base of b. Be careful of these common mistakes that students always make. We have got the inversion rule, although we can conclude it from those things above. Inversion rule. What do we have in inversion rule? I have got logarithm of b to the power of u with the base of b, that's always equal to u. Okay, so if this one and that one are equal to each other, I have got power of u, so the logarithm is equal to u. So we've got 7 rules for logarithms. Each one is of course useful in its position. Now we're moving to relationship between the graphs of logarithm of x with the base of b and y, that's equal to b to the power of x. Okay. Okay, when we were talking about exponential functions, okay, let me draw an exponential function, or first let me draw the mirror function. That is x-axis. Okay, that one is y-axis. That one is the mirror function y, that's equal to x. That is called the mirror for that case. Okay, and what are we concluding from here? Relationship between the graphs between the graphs of y that's equal to b to the power of x and y that's equal to logarithm of x with the base of b. Let's see the relationship between their graphs. We know that the graph of a logarithmic an exponential function is something like that. Okay, it's of course approaching to the x-axis, and that's passing through 0 and 1, that point. Okay, that's b to the power of x. There is a relation between logarithmic functions and exponential functions. Logarithmic and exponential functions are inverses of each other. And if you remember from the previous chapters, we've studied inverse functions. We know that if you have got two functions that are inverses of each other, so their graphs will be the reflection of the graph of f about the line y equal to x. What does that mean? Since I have got b to the power of x and logarithm of x, they are inverses of each other. I know that the graph of b to the power of x is like that. I will draw the line y that's equal to x, and that will be a mirror. Why do I say a mirror? Because the logarithmic function will reflect about that mirror. Okay, so how will the graph of this function be? It will be something like that. Okay, what's the reflection of 0 and 1? It is 1 and 0. Okay, since these two functions are inverses of each other, so their graphs will be the reflection about the line y equal to x, and that is the graph of logarithm of x with the base of b. Okay, that's the relation between those two functions. Okay, if you look at this function, we have got properties like we had properties for this exponential function. What do you see in that function? I see that it is smooth. Okay, the graph of the red one, the logarithm function, is smooth. Okay, defined for all x that's greater than 0, and it is continuous. Okay, the x-intercept, we have got in exponential function we had y-intercept, but here we have got x-intercept is equal to what? X-interception, it is 1 and 0, and the function is increasing. Okay, it is increasing when b is greater than 1. Okay, if that base is greater than 1, the function is increasing, and it is decreasing if b is between 0 and 1, like we knew for the exponential functions. Okay, the function is increasing when b is greater than 0, and it is decreasing if b is between 0 and 1. Why? Because the if b is between 0 and 1, the graph of the exponential function will be here, and the reflection will be something here. Okay, so these are the properties of the graph of the function or of the logarithmic function that we have got. Now we are coming to the natural logarithmic functions. What are natural? So far we have studied logarithmic functions. Now I'm coming to the natural logarithm. Let me write the name of it. The natural logarithm. Okay, in the previous lecture we studied natural exponential function. Okay, natural exponential function. What was natural exponential function? It was an exponential function, but the base, we had something for the base that was special. Okay, what was the base? It was e. Instead of saying 2 to the power of x, instead of saying 5 to the power of x, 10 to the power of x, we had a special base for the exponential function that was e, and the power was x. So that was the natural exponential function. Why? Because the base is the special number e. Here we have got natural logarithmic function. So what's the natural? We know that logarithmic function is logarithm of x with the base b. But if I make that base something special, if I give e to the base of the function, I will call that function ln of x. Okay, in general it's pronounced as ln of x, but in general we are saying what? Ln of x. So what is ln of x? It is the natural logarithm. Why is it called a natural logarithm? It's again a logarithmic function, but a special base is given to the logarithm. That's why instead of writing logarithm of x with the base of a, we are writing ln of x. Of course, ln of x has got the same properties as logarithmic functions. It also holds those rules, okay? Equality rule, product rule. For example, if I have got ln of u multiplied to v, it will be ln of u plus ln of v. So all of the rules of logarithmic functions applies to the natural logarithmic function. Why? Because the natural logarithm function is again a logarithmic function, but something special has happened to it, okay? So let's move to the examples that we have got. Example 4.2.5, it says evaluate or find each of the followings, okay? I have got A, that's equal to ln of E. That's equal to what? Let's evaluate it. I will write it in black color. Ln of E is equal to logarithm of E, and the base is E, because ln, I know it is logarithm with the base of E, and that E is in here, so I will write log of E is equal to E. If I have got those two numbers equal to each other with the rules of logarithm, if the two numbers are equal to each other, what does that equal to? That's equal to 1. So what is ln of E? Later on you will learn, and you will not need that step. You will know that ln of E is equal to 1. Okay? Second one, or let me write B, ln of 1. Ln of 1 is equal to what? I have got a rule for 1 in the logarithmic functions. I know if logarithm of 1 with any base is equal to 0. Ln is the same thing as logarithm, so ln of 1 is again equal to 0. Why? Because that one is equal to logarithm of 1 with the base of E, and I know that this one is equal to 0, but you do not need to write this step because you already know that ln of 1 is equal to 0. Part C, I have got ln of square root of E. I know that there's a relation between ln and E, but I have got a square root here, so I have got to get rid of that square root. So that one is equal to ln of e to the power of 1 over 2, okay? I will change the square root into e to the power of 1 over 2. And I know that in logarithms, if I have got a power, it comes in front of the logarithm, okay? Here we have got the power rule. If I have got something to the power of logarithm of u to the power of r, that r comes in front of the logarithm. So here what do I have? I will have 1 over 2 ln of e. We found ln of e, and we know that ln of e is equal to 1, so that one will equal to 1 over 2 multiplied to 1. 1 over 2 multiplied to 1 is equal to what? It's equal to 1 over 2. How about part D? I have got ln of 2. It's equal to what? We do not have a rule for this one. We need a calculator. Okay, since calculators are not allowed for you, so you're skipping this one. Okay, now we are given another example. That was page 22. Example 4.2.6. We have got 3 parts in that example. The first one, it says find ln of square root of a multiplied to b if ln of a is equal to 3 and ln of b is equal to little 7. Let's find that one. So this one is required from us. We have to find that expression, but 2 things are given to me, okay? Let's start with the solution. What do I have to start with? Ln of AB. I have to separate it. Look, I'm not writing directly instead of ln of A 3 and ln of B that's equal to 7. So 3 multiplied to 7 is equal to 21. No, why? Because here ln of A multiplied to B under the square root is given to me. How can I directly input 3 and 7 into that one? I have to separate that whole expression to ln of a, something like ln of a plus ln of b minus ln of b, or anything else. Then I can put instead of them 3 and 7. Okay, let's first get rid of that square root. I know that this one is a multiplied to b to the power of 1 over 2. Square root changes to 1 over 2. Now I have got a power. Power comes to where when I'm calculating logarithms? It is coming to in front of the ln. Ln is again a logarithm. That's why I'm bringing it down. So that will be ln of a multiplied to b. Okay? Now, this is multiplication between them. And I know that according to the product rule of logarithmic functions, product changes to what? Changes to addition. So that one is equal to 1 over 2 ln of a plus ln of b. Okay, look, multiplication changes to addition. Now I have got ln of a is equal to 3 plus ln of b is equal to 7. So that one is equal to 1 over 2 multiplied to 10. That is equal to 10, and the result is equal to 5. Okay, so what did we do? First, we expanded that expression to something like that, and then we could put instead of ln of a 3 and ln of b 7, or else we couldn't have done that. Part B, it says show that ln of 1 over x is equal to, okay, that's, you can put it in the parentheses, minus ln of x. You can solve this one in 2 different ways. I will do one for you and you will leave the other for you, of course. How can we, when it says show that something is equal to another thing, we know that we have to start with this one and get that side, or we have to start with this side and get that side. So let's start with this. Ln of 1 over x. What does that mean? I know that division changes to subtraction, so that will be ln of 1 minus ln of x. Ln of 1 is equal to what? Is equal to 0, because logarithm of 1 with any base is equal to 0. So that will be 0 minus ln of x. 0 minus ln of x is equal to what? Is equal to minus ln of x. Part C, it says find x if 2 to the power of x is equal to a to the power of 3. How do we solve this one? Look, if you look at here, x is at the power and the bases are not equal to each other. Previously, if we had the bases were equal to each other, we could say the powers are equal to each other. But in a case like that, where the powers are not equal, the bases are not equal to each other, what shall we do? I'm taking ln to both of the sides of the equation. Okay, I'm taking ln for both of the sides. So that will be ln of 2 to the power of x is equal to ln of e to the power of 3. Okay, look here, I'm not multiplying the ln to this side and that side. I'm putting that 2 to the power of x inside the ln, okay, and e to the power of 3 inside the ln. If you look at that expression, ln 2 to the power of x, that's a power, it comes in front, so it will be x ln to the power, x multiplied to ln of 2. Ln and e are inverses of each other, so they cancel each other. Okay, what remains here? 3 comes in front. Okay, so that will be 3 multiplied to ln of e is equal to 1, so that will be simply 3. Now I'm searching for x, so what do I have to do? I have to divide both sides by ln of 2 to get rid of that ln of 2, because I'm searching for x. So x is equal to what? 3 over ln of 2. And I'm leaving that like that because I do not have a calculator. We do not have a calculator with us. We have got, this was the examples, we have got a relationship between e to the power of x and ln of x. Okay, let me write relationship between e to the power of x and ln of x. What's the relation? The relation is that they are inverses of each other. Since they are inverses of each other, so I know that e to the power of ln of x is equal to x, Okay, of course, x here is greater than 0 because of the len. And I have got ln e to the power of x is equal to x for all x. Okay, so I've got two things related to e to the power of x and ln of x. I know that these are inverses of each other, so e to the power of ln of x will result in x, and ln of e to the power of x will result in x. Now we are coming to solving of the examples that are given in the material.